Hello, my name is Greg Peterson. I am a principal consultant with ScaleSec. We are a boutique cloud security and compliance company. And I live in the DFW area. I've been doing IT for about 30 years, 25 of it in security. Have a bunch of certs. I listed some here, probably got about 10. PCI has been a big focus for me. I've actually been at a major card issuer. I've worked for a major processor. I've worked for a credit bureau. I have a pretty good background in financial services. And today I'd like to talk to you about quantum computing and how it's going to affect cryptography in the future. So what we are going to do is explain what quantum computing is. We're going to say how it actually affects the world. And this is a thing that's coming. This is not science fiction. And then we're going to talk about how it's going to affect cryptographic standards now and in the future. And then what we must do to get ahead of the curve and how we're going to get regulated around this. So what is quantum computing? To start with, traditional classical computing uses bits. So it started with switches that turned on or off. These switches will basically represent a 0 or a 1. That's what we use right now on bits. Bits are 0s or 1s. And if we put 8 of the bits together, it becomes a byte. And that's how we do our regular computing. If we do quantum computing actually uses qubits. Qubits are kind of like bits, but different, fundamentally different. So they do have 1s and 0s, but they have superposition. This allows qubits to actually be 1 and 0 at the same time. It vastly increases the processing power. We also have what's called entanglement. It's not a big concern about what we're talking about here, but basically you can have 2 linked bits, qubits, and they will actually be at the same state no matter where they are in the universe. They could be on the different side of the universe, they could be in your hand, but they will always represent the same state. So what does this mean? What is quantum computing? Why does this matter? It fundamentally changes the way that computing works. Mathematical problems that used to be very difficult start becoming easier for computing. And that's a concern because cryptography is based on the fact that mathematical problems can be difficult for a computer to actually solve. So what we're going to do is talk about how this works. I have some mazes here, and the mazes, basically there's an analogy that if you are using classical computing and you do a maze, the computing will actually send an agent down one of the paths. If it ends, then it'll send it down another path. If that ends, it'll send another path until it actually finds the end of the maze. Then if you actually want to find the shortest route, it's going to have to go down every single path to see what the shortest route is. That's how classical computing works. In quantum computing, as soon as the agent gets to any sort of split, it's going to send another agent that way. And it's not really an agent, it's itself, because it can superposition itself. And then every time each of those hits another split, it's going to go down that route and split itself until you have multiple qubits heading all the way down to every path until it gets to the end. The first one that actually gets to the end will prove that not only this is the path, but it's the shortest path because it's the first one to get there. So what quantum computing does is in the amount of time that classical computing may actually send a bit 2 or 3 places, the quantum computing could already solve the maze. That's just an example of the fundamental difference between the two. So what's the impact? The impact, there's lots of impacts about quantum computing. We're going to focus today on public keys. So public key cryptography is very common in use today. What public key cryptography does is you create a private key, and this is something that whoever creates it protects and holds, and then we use math to create a public key. There's a correlation between the public and the private key. If I encrypt something with a private key, it can only be decrypted with my public key, and vice versa. If somebody encrypts something in a public key, it can only be decrypted by my private key. So I have a picture here, an example. When you have a private key, it uses math. It takes 2 large prime numbers, and prime numbers can be only divided by 1 in themselves, and it multiplies those together and gets a large number that's used to create the public key. This is easy for classical computing. It can actually calculate this. The hard part in classical computing is to take that large number in the public key and factor it back to 2 prime factors. That is very difficult right now, and all cryptography is based on how difficult it is to decrypt something. What quantum computing does is it makes it much easier for it to actually recalculate back and to figure out what your private key is from your public key. This is a fundamental threat to the way we currently do cryptography. So let's talk about this a little bit more. How is this going to affect your business, your organization? We use a lot of technologies that use public key cryptography. The main one that I want to focus on is TLS. So it's transport layer security. We use that as HTTPS, so your browsers, your apps, APIs, all use that. APIs are important because anything that's a SaaS solution or anything in the cloud, Google Cloud, AWS, Azure, they all run on APIs. Everything is using TLS. TLS is at threat to the fact that this can actually be decrypted in the future when quantum computing gets to a level, and we're going to talk about that in a minute. Other things at threat would be VPNs, code signing, digital certificates, and blockchains. All of these rely on this public key cryptography. What are the impacts of this? The first is going to be data confidentiality. So once again, if they can break your encryption, they can actually read what's out there. Your data integrity. If you're using code signings, if you're using digital certificates for logins, all of those could potentially be compromised, and people could either fake your code, they could get unauthorized access, something along those lines. And then you have compliance and trust issues, compliance frameworks. Most of them say you need to keep up on cryptographic new algorithms, everything that's coming out. And if you do get breached through this, you're going to have loss of trust. And then the final one that I do want to mention, because people don't think about this, is there's a strategy on harvesting now and decrypting later. So right now, and we'll talk about that in a minute, quantum computing is not capable of decrypting public key, but in the future it will be. So a lot of organizations, governments, criminals are gathering data. They're just recording information with the hopes that in 5 or 10, 15 years, they can decrypt it. So there's a big concern on focusing on having data that is valuable to not go through something that can be decrypted in the future. So if it's something that, let's say, has a short life of 1 to 2 years and it's not valuable, that might not be a big concern. If it's PII, if it's PHI, financial information, if you're sending the secret to Coke's recipe, that is a concern because they can wait 10 years to get that. Let's talk about the current state of where quantum computing is today. It exists. So quantum computing exists today. We'll talk about that in a minute, but it is not in a state where it can actually break public key encryption. It is basically developing as we speak right now. So the industry is focused on getting it stable and building larger, more complex quantum processors. What's the timeline that we're worried about? So governments, and this is timelines around breaking public key encryption. Governments and nation states, the expectations are in the next 5 to 15 years that they could actually start breaking it. We don't know because they're never going to publicize this. We're pretty positive they can't do it right now. They are for sure harvesting data right now, but we will probably not get an announcement when this happens. But the big areas of the world that we're seeing this is the US, the EU, China. They're all heavily invested in this. Where's industry? Right now, industry will probably get major breakthroughs maybe 3 to 5 years after the government gets to the point where they can decrypt this. And there are offerings out there. You can go to any of the cloud providers and actually test algorithms on quantum computing because it does exist, just not at the levels needed for breaking public key encryption. And then criminals, when are they going to get this? Well, as soon as it's easily available and affordable, or they can steal it. That's really the case with criminals. So if we go off to the next slide, we will talk about how government and industry is responding to this. So PQC is post-quantum cryptography. Government is issuing standards right now. So in the US, you have the NIST, NSA, and CISA. They have all issued standards around this. EU is doing the same. They're giving guidance, migration planning on migrating away from these vulnerable algorithms into these algorithms that are post-quantum cryptography. And roadmaps, there's mandates on timelines. So NIST came out basically saying a lot of what we do with TLS, and I'm going to get a little technical right now. So we talked about TLS as how the internet works right now. TLS uses what's called asymmetric encryption versus symmetric encryption. Symmetric encryption is basically having both sides of a conversation having the same key. And that is actually fast and secure. So an example would be, let's use Walmart. Walmart has their headquarters and an office. If they want to talk to the office encrypted, they could send a router out to the office with a shared key on it and use a symmetric algorithm on there. It's secure, it's fast. As long as they secure this secret that they've shared, it's fine. But when I talk to Walmart.com as a customer, I cannot share a key securely with them. They have no way of getting the share key to me. So we use TLS, and TLS has a handshake in front of it. TLS handshake basically uses my public key and private key, and Walmart, and when I say my, I mean my browser's public key and private key, and Walmart's public key and private key, and they talk to each other and negotiate to get this shared key that they then use for symmetric on there. What's vulnerable is TLS. The TLS handshake. So there are roadmaps and mandates on TLS stating that in 2030, the algorithms that we use right now on TLS version 1.3, those for the handshakes, those are going to be deprecated in 2030, and by 2035, they're going to be disallowed. So TLS will have to be updated, and version 1.3 and maybe 1.4 when that comes out, those should be able to support these new algorithms. Industry is focused on this. There's research. There are a lot of companies contributing. They're integrating PQC into their products. There's alliances out there, Linux Foundation and the ISAC, Financial Services Information Sharing. They all have different links, which I have here, that you can look at on what they've done. As far as timelines, where we're going, standards are coming out now. They're going to come out in the near future. Products, there's some now, as I mentioned, AWS, Azure, Google. You can all go on and do quantum computing right now. You can actually test your algorithms, but in the next 5 years, it's going to continue to grow. And then widespread adoption is probably in the next 5 to 10 years. I mean, right now you can go into Chrome, and Chrome actually supports some PQC, but in the next 5 to 10 years, everybody's going to support it. Guidances and best practices. So in the PQC world, NSA and CISA have provided some guidelines. I'm going to summarize these here, but right now is prepare now. So remember the harvest now, decrypt later. If you're sending stuff now, people can be storing that to decrypt later. So you really need to address this now, not when it happens. One of the first things you need to do is inventory your cryptographic assets. So not only should you know the systems that use it, the applications, and the data, but you need to know the algorithms that you're using and where you're using them. There's different approaches. There's a hybrid approach that's out there. It's kind of the belt and suspenders. So if you wear a belt or suspenders, so hold up your pants. But if you wear both, if one fails, the other's still there for you. That is the same approach with encrypting with TLS, as well as a basically PQC approved algorithm. You encrypt with both of them in case one of them does fail in the future, you have the other one. That is a way of approaching it, which some companies are doing. You need to prioritize your migration. So as you work towards migration and bringing in these new algorithms as they come out, you really should have a prioritized list. This is the most important, then we move to the next, then we move to the next. Another thing is adopting crypto agility. Crypto agility is the concept that your applications or products do not actively need a specific cryptographic algorithm in there. Instead, it's more of a plug and play. You don't hard code an algorithm. You basically hard code the function to an algorithm, and you let the algorithm be independent. You really need to be developing your applications this way. And then engage with your vendors, talk to them, see what they're doing in the future as regards to PQC. Most of them have a roadmap, and they will gladly share it with you if you contact them. User adoption. When we actually get to the PQC world, you got to worry a little bit about user adoption. One of the big things is browsers. So TLS is a huge part of this. As I mentioned, HTTPS uses it. The users may not update their browsers as quickly as possible. And so as an organization, you may have to support older browser versions just to support these customers, or delegate exactly what you're going to allow in as algorithms. So you do need to factor that in. If you're a big organization, you have a lot of legacy systems, your legacy systems may not be able to be upgraded PQC. And so you may have to migrate off of them, or you may have to wait till the vendor actually releases something. So that's something to concern yourself with. Skill gaps. As this comes out, nobody's really knowledgeable on PQC now because it's a new technology that not everybody's using. And that may be a concern in the future because your in-house staff may not be experts on it. They may require some training or upskilling, and you may have to bring in consultants to help you with it. So these are just challenges of going to PQC world. Action items for you. What can you do? So the first thing is cryptographic inventory. You need to inventory everything you have so you know what you need to change and what you don't. And since we're in PCI, DSS requirement 12.3.3 is actually requiring this. It wants you to inventory it and wants you to understand what's going on in the industry and then change as it goes. And this was mainly written in my mind to address post-quantum cryptography. So you have to do it in your PCI environment, but you really should do it in all of your environments. Assess risk and prioritize. You need to determine what your risky apps, what your risky systems are, and then you need to prioritize which ones you need to move forward. Because if your lifespan of your data is perpetual, that data can be harvested now. You really want to get to a point where that is not susceptible to quantum computing right now, or even in the immediate future. All right. And the last two, quantum roadmap. You really should have a quantum roadmap that you put together. This quantum roadmap will give you a migration plan, and it will actually help you put together a team. And some companies have their own analysts or architects that can work on this. Some companies may be one person, but really any organization needs somebody to look at this now. And once again, the harvest now, decrypt later is the big concern. And then educate your stakeholders. So most boards aren't aware of this. Most senior leaders may have heard of this, but they're actually not informed of what the risk is. So dealing with your stakeholders to be sure that they actually know what's coming and what the risk is around it. Make sure that you have funding for it and that you get the prioritization you need. And then talk to your vendors, and once again, see where they're going. With that, my name is Greg Peterson, Principal Consultant with ScaleSec. I thank you for your time and have a great day.